We have seen that the frequency selective surfaces can act as the band stop filters and band pass filters. So in this video, we are going to see how the band stop filter response will look like and the band pass filter response will look like. So in case of a band stop filter, if we are providing a range of frequencies, it will reflect some part of the frequency back and allow other part of the frequency to go through that. So let's see how it will look like in CST simulation. As we have seen is a square loop can provide the band stop filter. I'm going to create a square loop and let's see how its response will look like. So I'm not going to refer any particular design. I was just going to design some square loop and going to check that. So I select the frequency from 1 to 10 gigahertz and let's click finish. So as a substrate, maybe we can choose the FR4 substrate. So I'm going to create the substrate having the periodicity D and the thickness H, maybe H we can give as 1.6 mm. So where is FR4? Okay, FR4 low C. I have taken it. Then D, because I have taken the frequency from 1 to 10 gigahertz. Maybe let's check for 3 gigahertz. 3 gigahertz, the wavelength will be around 100 mm. So maybe we can uh, take the periodicity 20 mm, which is very less than the wavelength at 3 gigahertz, because for the periodic structures we have to take the periodicity as very less. So I'm taking 20 and thickness I'm taking it as 1.6 mm. So now we have seen that square loop can provide band stop. So I'm going to create a band stop. I'm going to create first square minus L by 2 to minus L by 2 to. So I'm going to create that on the top of the substrate, and maybe we can give the thickness of the metal as 0.035 and click PC. So maybe periodicity is 20. Maybe we can select the dimension as 18. And now I have to create the square loop. So I have to create one more square. So maybe I can give the name inner, and I am going to give the dimension as M2. Okay, so 1035. Okay, M. So we have given 2018, maybe 16 we can give. So it is coming inside. So now I have to create the square loop. For that I have to subtract inner from the loop. So I'm going to subtract. So now I have a square loop. Next in simulation I am going to give the boundary, because I'm using the time domain. I am going to use electric and magnetic. As this structure is symmetric, you can use the electric and magnetic in X or Y. And as it is a frequency selective surface, there won't be any metal so on the back. So I have to give open at space on Z min and Z maximum. Now we have to assign the waveguide port. I'm going to click OK. So in port I'm going to create the waveguide port. So has to be along the Z axis. So I'm going to create along Z axis, and now this port is assigned here. So I have to de-embed the port to the back of the metal sheet. For that I can check this value. This value gives the distance from here to the origin. So I can take this value And if I give this value here, um, you can see that. Okay, so you can see that the port is embedded to this position. So I have de-embed the port to that position, and then I have to click means create another port on this axis. So I'm going to create that, and this distance gives the distance from here to the 0 position. So I'm going to take this value, and now you can see the port is de-embedded to this position, but I have to de-embed the port to the top of the metal. For that, I have taken this value, and I'm going to calculate the distance to that position. So as I know the distance from here to here as 15.2, if I want to get the distance up to this point, this 15.2 minus h, that is the thickness of the substrate, minus h, that is the thickness of the metal plate, that will give us the distance from port to this top position. So I'm going to give minus h minus 0.035. Sorry. So if I click preview, you can see that port is de-embedded to that point. So for port 1, okay, port 1 and port 2, you can see the ports are de-embedded to the structure. So this is one of the important parameter you have to consider. That is, port de-embedding is very important while doing the periodic structure simulations. So that's all. As I'm not going to check the accuracy, I'm not going to check any mesh settings or anything. I'm just going to do the simulation. Okay. So it may take time. Let's wait. Okay, now it's calculating. Okay, so now the simulation is complete. If we go to 1D result and S parameters, you can see the S11 and S21. So here, this red one shows the S11. This you can see that S11 is showing 0 dB. That means that there is like it is getting reflected back from this frequency. It is like this frequency range, it is getting reflected back, and this is the transmission. Green line is the transmission. You can see that maybe from this frequency to this frequency, you can see that it is that is from 2.3 to 3.74. You can see that the transmission coefficient is less than minus 10 dB. That means that in this frequency range there is no transmission, and all the waves are getting reflected back. And after that, above and below that frequency, you can see that the transmission coefficients are more than minus 10 dB. That means it is getting transmitted. But in this frequency range, it is not getting transmitted. All are getting reflected. So this is the band stop response. So this is how the band stop response will be looking. The S11 will be showing the 0 dB values, and S21, that is the transmission, will be showing the value like means which is less than minus 10 dB. So this will give us the band stop response. So next we can see what will be the band pass response. For that I am just trying to copy these response here so that I can have a comparison. So I just copy this value. So this is for S11 band stop. I'm renaming this for the comparison purpose, and this is S21 band stop. Okay, so now we have created from the square loop, we have seen that we can get the band stop response like this. So now we can check what will be the band pass structure. So if we take the dual of the structure, that is now we have considered the square loop, and if we take the dual, that is replace this metal and use the metal on other parts. This is the dual of this structure. So if we take the dual of the structure, we should get a band pass filter. So let's see how I can take that. So now I'm just going to maybe say yes, band pass. I have saved it as band pass, and what I'm going to do is I have to take the dual. So for that maybe I will delete all the result, and what I'm we have the result means previously simulated results are here, so we can have a comparison. So what I'm going to do is I'm going to model a um, to take the dual. I'm going to create another I'm going to create another square. So let's take another square. Minus d by 2 to d by 2. Okay, then click OK. So if I want to have the dual, I can subtract that loop from this solid. So now I get the dual. You can see that this structure we have created now. So we have the dual. So our means expectation is we have to get a band pass response from this structure. So I'm just going to check whether the ports are okay, as I haven't changed the frequency. The port de-embedding will be okay, and I'm just going to start the simulation. So it may take some time. Okay, let's see what is the S11 and S22 response. So here you can see that the S11 is showing the dip. That means it is getting transmitted. But when you see the band stop characteristic, you can see that S11 for the band stop will be showing the 0 dB value. And if it is like a band pass, you can see that it is getting less than minus 10 dB. So I'm going to just copy this also here just for our better comparison. So this is S11 for band pass. Okay, band pass, and this is S21 for band pass. So, so okay, so this one band pass. So this will be the band pass response. You can see that the S11 will show the 0 dB and S21 will be, sorry, S11 will be showing less than minus 10 dB values and S21 will be showing 0 dB values. This means that at this frequency range, like from here to here, the frequency is getting transmitted. So this is the band pass response. So if you compare the band pass and band stop, you can see that, okay, maybe it's cluttered. So I will take the S11. You can see it becomes dual. For the band pass, S11 become less than minus 10 dB. For band stop, it will be 0 dB. So this is how the response of band pass and band stop will look like. So it will look like the reverse. So now we have seen that from the square loop we can get a band stop, and if we create a dual of that we can get a band pass response from that structure. I think that's clear. So this is how we are creating the band stop and band pass FSS structure. Thank you. So in effect, this is the response of the bandstop filter. So if we have a square loop, we will be getting the response like this. S11 will be showing the 0 values and S21 will be showing the values less than minus 10 dB. And in case of a bandpass filter, if you have a dual of square loop, it will be like this. This S11 will be showing the less than minus 10 dB and S21 will be showing the 0 dB values. That's all. Thank you.